Okay, so we will proceed with the implementation, and I will show you a tutorial how to use the system, how to try on things with it. And here we go. If the system is started, this user interface shows up, and this user interface serves multiple purposes. One purpose is to be able to input statements into the system. Another purpose is to see the entire system state in a single visualization, which made it for us a lot easier to see potential issues and problems. And so, let's start. Here at the top we see the little user interface, which is for different purposes, like starting the inferencer, stopping it, applying single steps, changing the speed of the reasoner, resetting it, saving the entire system state to a file, loading that file, and then some user interface specific functions like inverting the color. Then a priority threshold, this one I will show you later where this one is used, and further details can be shown when this button is pressed. So the buttons above are following with the user, which is very handy, like you will see. Here you see a diagram of the entire implementation. And this diagram shows all the different actors which were needed in order to implement this system. And these actors play different roles. Like it should be able for concepts to form, for new tasks, for new statements to enter into the system, so that so the tasks can be created based on this new statements, and that concepts can be created based on them, and the tasks entered into the task bags in the concept. And the reason why we went for such an actor-based design is that NAS is in principle very nicely distributable, because the concepts in the system act as own local processing units in the system, in the memory of the system. And so let's give an example for this. Let's say the penguin is a bird. So we send this to the reasoner, and we see what's happened. At first it went to the sentence parser. The sentence parser sent it to the task creator, which created a task for it. And then the task dispatcher dispatched this task into memory. And what we ended with can be seen on the other side. There's now a concept for bird, a concept for penguin, and a concept for what we entered. The penguin is a bird. What we see here is that also our input task made it into the concept. Here we see the entire task back visualized, and currently there's just one task in it. So this is, if you try on experiments, you can easily show, if you enter, you can easily see if an input statement is still in the back, because it can be that the system derived new knowledge and decided that there is something more important than what you input. Can happen. And here you can check what is really still in the concept. And to go back to our example, to show how we can reasoning, how we can how the system can apply reasoning now. There's an output rectangle, and in this output rectangle we see what happened so far. We input a statement that penguin is a bird, and it's entered the default confidence value for it, and it has a frequency of 1 because there is only positive evidence. If we now say that bird is an animal, and we send this, now we have two tasks. Penguin is a bird, and bird is an animal. And if we now apply the step button at the top, we will see that the system begins to derive new knowledge from what it got so far. Here we see that the system began to believe that the penguin is an animal. This was applying the deduction rule on our input. More interesting for many people are cases like the abduction rule. Let's reset it. And let's say, for example, that dim is an instance. This is why we read it this way, because it cannot be further specialized. So if we say, for example, dim quacks, and we say additionally duck quacks, then we see a first use case for the abduction rule. Let's send this to the system. I click too often, but here we go. It believes that duck. Oh, this was not the conclusion I searched for. This one is this one. It believes that dim is a duck because dim also quacks. The duck quacks, dim quacks, so dim might be a duck. So it already has found a certain pattern in its experience and has used this pattern to derive new knowledge. And so what we saw so far is how to enter statements into the system and how to derive that the system derive new things. Where to proceed? So if we go back to the concept graph, now there are already a lot of concepts, and nearly all of them are not directly our input statements, but concepts which were derived from our input statements. And this is one nice property of the system, that it begins to create concepts which summarizes its experience. And here you can also see that the concepts are usually connected based on the semantic relationship. For example, duck quacks is surely connected to the concept duck. There is also the possibility to filter concepts. If we go to this concept back window and enter duck, now it will only show us concepts which are related to duck. And so we can filter this concept graph for different things we are interested in, which also makes it much more easier to see what knowledge, what derived knowledge does the system have about a certain topic and about a certain term. Additionally, there's a priority threshold option on the top of the graphical user interface, and this does the following. the concepts, as we already said, they don't have same priority, but which concepts currently have a high priority depends on the current context. And so they are all ranked, they are ranked in the back, have different priorities, and if we are, for example, only interested in the concepts which have a certain priority, then we can increase this priority threshold value, and it will begin to only show us the concepts where the system thinks currently that they are more important. Right. So this gives a nice way to see whether the concepts one expects to be important for the system, if the system also thinks so, or if there are other concepts it evaluates as more important currently, can be nicely evaluated with this concept graph. Another thing which you might see here, there is a link. I don't think this is necessarily visible, but there's one link, there's the concept dim, and this concept dim is, in this case, okay, let's choose another one. My point is, concepts link to each other, but not necessarily with the same link strength. So it can be that a certain concept prefers to interact with another, while the other one does not prefer to interact with the first one. And this has multiple reasons why this is a good idea. The best aspect about it is attention related, because attention should be directed. And so this, what we already see here is that the system directed relationships between concepts. And as we also discussed, because of the assumption of insufficient knowledge and resource, it is the case that a concept, it can't have arbitrary amount of links. It has to choose which other concept it decides to interact with, based on multiple criteria, like did the interaction with the other concept lead to an relevant result, to an important result, or result of high quality, and everything this is concerned handled. Next thing, I can show you an interesting decision-making task, because for me personally, the question answering is already nice, but it's even better to have the system to apply creative decision-making in order to find a solution to a problem. And this is especially interesting with the system because the system might not know a lot about certain coherences it has to use, and so it has to try different options, and we will see one of these examples. And it's called the toothbrush example. I just want to scroll because I don't want to show you the entire solution already. Let's say we know some pieces of knowledge already, like that a toothbrush is made of plastic, that hardened objects in the right shape might be able to unscrew our screw, that plastic can be melted, that if something is melted, it is pliable, that heat causes things to melt. So different pieces of knowledge. Here in this example we assume that the system already has certain opinions on different relations for objects, and the question is for the system, it should unscrew the screw with the options it has available. And there are different options it can use, and in the end the system should, by reasoning, apply the decision-making process, which looks as follows. At first, the toothbrush, which is made of plastic and can be melted. Probably it makes sense to use the lighter, which generates heat in order to melt the toothbrush. Since the toothbrush then is pliable, it can then be reshaped. So the system then has to reshape it and let it cool in order to be finally able to unscrew the screw. So this is also interesting. It also compares to some animal experiments where the animal has to use certain steps in order, some creative steps, and has to find out how to get food, for example. And we can simulate this example with the system. I won't go into the details here. So this is also one part of the user interface. If one has examples like in a text file, it's possible to just copy it, and then when the paste button above is pressed, it will automatically input whatever is in the copy-paste buffer. So we paste it now, and the system will begin to try to solve this problem. We will also set it to fast mode in order to be a bit more effective here. And it begins. The system, we can see, for example, we can filter the output for toothbrush in order to see what the system reasons currently about it. It was probably already too fast because it already, let's slow it down, I stopped it. It already derived that the toothbrush might be the solution to the problem, that the toothbrush, that it should somehow make the toothbrush pliable, and that it should, after it's pliable, reshape it in order to be able to reshape it into a form with which it can open the screw, unscrew it. And it was already pretty fast. Didn't expect this, because sometimes it takes longer. And what we soon will see, it's still thinking a lot about the toothbrush, as we see here. Constantly new tasks arrived tasks, but I think it already did it. Oh, in fact, it already did both things. It applied the lighter to the toothbrush in order to melt it, and then applied the reshape operation to the toothbrush, because it thinks if it is reshaped, it might help it to unscrew the screw. So it has successfully applied, has successfully achieved this decision-making problem. This is actually the one which was suggested by relational brain theory, which is also a nice example, because the system, we didn't need to adapt it for it. The knowledge which was represented in this example was easy to represent in the non-axiomatic logic, and this was everything for the system in order to deal with this example. This is what we have. Another thing, because there still seem to be 10 minutes left, is this right?
Yeah.
I think so. Then we can also try a normal question answering example. And there we have some interesting domain, and it's detective domain. Imagine you are a detective, and there are multiple people claiming different things, and you have to decide who is the murderer. And you have to summarize the different evidences you get from different people, and you have to judge on your own. And often this is also a nice example which shows that in a real world you are often challenged by conflicting evidence. If one person says this and the other person says the opposite, we won't go crazy. We will summarize this experience and work with it. And this is also what's happening here. Here the detective gets multiple informations, like that Tim lives in Graz, that sorry, that Tim lives in Graz, and another person says, no, this is not even the case. Another one has some subjective judgment and says, people with sunglasses tend to be aggressive. And another person says, aggressive people tend to be murderers. And one says, I know, that Tom owns sunglasses. And the system now has multiple evidence, and we can ask it, what do you think is the murder? And it summarizes all these different evidences. Let's reset it, but before let's have one look at the graph, because it was, let's correct it. Does it not visualize it? No, it doesn't matter. Let's reset. Let's go for this detective example. Copy. But at first we will filter the output for answers, and this is possible by just typing answer, because answers are marked as answers. So we will filter the output because we are only interested in the answers. And let's ask the system what it thinks it is, what it thinks that the murder is. Let's go to slow mode. Slow mode. Copy. Paste. Currently the system is started, or the things they're going in. In case that you wonder why there are exceptions, it's because of the comments, because those are not necessary statements. Those are not null statements. So the system, probably it's more interesting to see what derives. Here it derives